Hey guys, so this is the video for solving the problems that I gave to you for your midterm review. Alright, so this is ch112. Midterm review. So, I don't know where my words just went. So what I'm expecting is that you've already tried the midterm maybe a couple of times. You've worked out these problems, and then now you're trying to figure out whether you've done them correctly. If this is the first time you've encountered these problems, it's not the best way to study. So you're going to want to stop the video and go take the midterm example that I gave you and then look at this. Alright, so for number 1, it says that 2 5-liter containers have 0.93 moles of hydrogen gas. Okay, so this is going to be a gas problem. So immediately I'm going to look at my handout, my formula sheet that you get, and I'm going to look for all the things that are gas problems. And let's see, and I try to start assigning variables. So when it says 2 5-liter containers, so we've got a volume of 5 liters. It's just looking at the unit. I know that liters is a volume. So I'm going to assign that to V. And they both hold 0.93 moles. Okay, so in gas problems, moles are N. So I'll put that. And it says hydrogen gas, so that's good to know. H2 is hydrogen gas because it's diatomic. And it says if container A has a temperature of 20 degrees Celsius, so temperature of A is 20.0 degrees Celsius. Now, I remember from gas laws that usually we have to add to get to Kelvin if it's in Celsius. And this is 0.2 because it's actually 273.15, but I don't have the hundreds, I only have the tenths place, so it's going to round up to 0.2. Quite frequently people forget that it's not just 273, so that's something to pay attention to. And so we're going to get 293.2 here. Kelvin is the temperature in container A. And B is 400 Celsius. Wow, so B is a lot hotter. You know, so that's going to be, oh, it doesn't say 0.0. Oh, I messed it up. Wait. Oh. Okay. Fixed it. Alright, so 273 plus 400, of course, is going to be 673 Kelvin. So container B is a lot hotter. And I know that when gases are hot, they tend to expand, so meaning the volume would be bigger, or be under a higher pressure. One of those two things has to be true. Because they're moving around so much faster. So then it says container A is bigger than container B. Well, the question said that 2 5-liter containers, so they're both, A and B is 5 liters, so choice A is probably not good. Container A has more energy than container B. Okay, that would be true if container A had a higher temperature, but it doesn't. So B is not it. Container A and container B have the same energy. Well, that can't be true. If they have different temperatures, they have different levels of energy. And container A has less energy. Okay, so it's got to be D. And so when we talk about energy, we're sort of picturing if we have a sample of gas at 293, which is room temperature, they're moving pretty fast. They're pretty far separated. But if we heat that up to 673 Kelvin, they're going to be moving a whole lot faster. And when things move faster, that means they have more energy. Okay. Number 2, a balloon. Okay, so another gas problem. A balloon has an initial volume of 4.1 liters. So again, I'm trying to assign my variables. That would be the volume, because it's in liters. And the pressure, it says 1.5 atmospheres. 1.50 actually. Just to keep our sig figs straight. If the balloon is squished, so the volume is okay, so this is the initial volume, V1. And V2 would be smaller since it's being squished. It's going to be 1.9 liters. And it wants to know the pressure. Okay. So this initial pressure is this one, and we're looking for the second pressure. This is going to be a Boyle's Law problem. So on our formula sheet, we have this. P1 is 1.5 atmospheres. V1 is 4.1 liters. They go together. Those are our initial conditions, so I know they have to go together. And we're solving for P2. Alright, so to do the math here, first I'm going to multiply on the left. 1.50 times 4.1. we get 6.15. And those units don't cancel, they're weird. They just combine together. And then to get rid of the liters on this side, I have to divide both sides by 1.9. So it's going to be that number divided by 1.9 will equal our pressure. And I know it's division again because I'm multiplying P2 times V2. Alright, so P2 is 3.2368. I've only got 2 sig figs, so I guess I'm going to go 3.2. And that would be atmospheres because the liters cancel out. And, okay, so in our answers it looks like the sig figs are different, but A is the best answer. It's the closest to the correct answer, so we could go with that. Alright, so number 3. Oh, I didn't write the answer here, so it's A. So number 3. What volume of HI will be produced if 4.12 milliliters of hydrogen gas is used in the following reaction? Okay, so there's a couple of ways to answer this question. We can assume that they're talking about conditions that are standard temperature and pressure, which we should recall means the temperature is it's 273.15 Kelvin, so exactly 0 degrees for gases. And the pressure is 1 atmosphere, which is, you know, you can find equivalents for that elsewhere. Also, we can remember this fact. So I just Googled this to show you, but it's in your notes too. If we are at standard temperature and pressure, we can write a relationship. 1 mole of a gas is 22.4 liters. So 1 mole equals 22.4 liters. So if we assume that, then I don't need to go through a stoichiometry calculation like with moles and the molar ratio and molar mass and all that. All I have to remember is that there is 22.4 liters for 1 mole of any gas. Alright, so if we have 4.12 milliliters of hydrogen to begin with, first off, gases are usually in liters, so I'm just going to go ahead and do that. Yeah. So we got that many liters of H2. And so this question is asking, oh, it's asking how much HI is produced. So we actually do have to go through a stoichiometry problem. But I can still use this relationship to get it out of moles, right? So that many liters of H2. I'm going to flip that relationship over so I can get it into moles. So there's 1 mole of that for every 22.4 liters. So there's way less than a mole here. What I'm putting in the calculator is 0.00412 divided by 22.4. And I know I have to put the 22.4 on the bottom because I got to cancel our liters. And so you get a really small number. This might come up in scientific notation in some calculators. I have 3 sig figs, so it says 1839, so I'm going to go 184 moles of H2. Okay. Now, this, I'm going to use the balanced reaction in the problem. It says there's 2 HI for every 1 H2, which makes sense. You got 2 hydrogen, okay? And so we would be producing 0.000368 moles of HI. And then I get to use the same kind of relationship here to convert it back into liters. Well, ultimately milliliters. Oh, I did that upside down. Hang on. I want to get to liters, so I'm going to put moles on the bottom so that it will cancel here. Now, gases are cool because when you do a completely gas phase reaction, you don't actually have to convert it from liters to moles. You could, you know, because this is a multiple choice question, we're not having to show any work or anything. You could simply realize that the ratio of HI to H2 is 2 to 1. And so then you could go from 4.12 milliliters of H2 and kind of just go directly here, since these two sort of undo each other. Yeah, so I got that off a little bit, but in order to get it back into milliliters, we'd have to multiply by 1,000. And so then the best answer here is going to be B. Let me get this thing out of the way. Okay. So a little shortcut we could do is just to use the molar ratio here, because gases, assuming the temperature is not changing over the course of the reaction, the gas volume mole relationship is going to be consistent. Now, if we had a situation where the question said that maybe the reaction was exothermic, let's say, so it's heating up as we produce product, then I could not make that assumption. I would have to go through a bunch of ideal gas law calculations. So that's something worth paying attention to. Question 4, which substance would be the most soluble in water? Okay, so I'm just going to write these down. All right, so to figure out solubility in water, what we're trying to find is something with similar intermolecular forces. So this is really an IMF question. So I always start by identifying, pretty much anytime they ask me for a physical property, whether it's mixing with water or solubility or boiling point, melting point, any of those kind of questions, I'm going to have to involve intermolecular forces somehow. And of course, our 4 forces are London dispersion forces, dipole-dipole, hydrogen bonding, which isn't really a bond, it's a lie, and ion dipole. And that was in order of increasing strength. So LDF is lowest, ion dipole is the highest. All right, so basically the way to tell if something has only London dispersion forces is if it is nonpolar. In other words, if its shape is symmetric. Remember, symmetric, nonpolar, asymmetric, polar. SNAP. Okay, so CH4 is 4 domains, no non-bonding domains. That would be a tetrahedral molecule. That means it is symmetric. So it's nonpolar, which means that its intermolecular force is London dispersion. Oh, HF is hydrogen bonds, because if you have H attached to fluorine, oxygen, or nitrogen, then it counts as an H bond. Those are pretty strong, pretty polar. Hydrogen and chlorine are going to be a linear molecule, but they're not symmetric because hydrogens are little and chlorines are big. So that is going to be a dipole, which is not as strong as a hydrogen bond, but pretty strong still. And then here we got a whole bunch of carbons and hydrogens. Each one of these carbons is tetrahedral, which means symmetric. So that's also going to be London dispersion. I'm going to guess since A and B are the same, they're probably not the right answer. And that would be true because London dispersion forces don't mix well with hydrogen bondings like what water have. Dipole-dipole does mix pretty well. HCl does dissolve in water, but hydrogen bonds mix even better because they're more similar to water. Hydrogen bonds in water, hydrogen bonds in HF, so they mix together pretty well. So I'm going to choose B. Question 5. Let me turn my cursor back to a normal color. Question 5 says, which of the following is the most polar? Okay, so another LD, like IMF question. So here's the choices. And actually, it's not really an IMF question because it's asking about the bond. It says, which has the most polar bond? If it was asking which was the most polar molecule, then we would have to use IMF. For the bond, we're going to use electronegativities. And the thing is, I don't actually have to calculate the actual value. We can look for the trend. So if you recall, the trend is that electronegativity increases to the going like towards fluorine. So francium is the lowest and fluorine is the highest. So we're kind of looking for the two atoms to be as far away from each other as they can be. All of them have hydrogen in common, so that's interesting. So H and F are pretty far apart, so that's pretty polar. HCl is pretty far apart, but Cl has a lower value than H does because it's farther down. So that means HF would be more polar than HCl is. H2O is really HO, so it would be comparing oxygen and hydrogen. They're closer together, so they're not as polar as HF is. And carbon's even closer than that, so that's pretty much non-polar compared to the other three. So the best choice here is HF because it has the biggest difference in electronegativity values. Alright, so for number 6, this one is got a phase change diagram on it. We called it a heating curve. And I can tell right away this is not water because it has the first plateau, the first phase change occurs at 40 degrees and the second one occurs at 80 degrees. Water would be 0 and 100, of course. Oh, the numbers got messed up. Well, okay, so it's labeled number 4, but it's supposed to be number 6. It says, what temperature was the sample when the solid and liquid phases were both present? Oh, alright, so that happens when things are melting, going from a solid to a liquid. Or when they're freezing liquid to solid. That's the first plateau. So if I sketch this here, well, not sketching it very well, this is the melting point / freezing point, and that's where the liquid and solid occur together. That temperature on this particular chart is 40 degrees, so I'm going to choose A. The next question, which is, I'm just going to label it how I did on the thing, is question number 5 again. Based on the heating curve, which statement is true? The freezing point of the substance is 0. It's not. It's 40, so not A. The heat of vaporization is larger than the heat of fusion. Okay, so we would want to compare the size of this space. Here's your fusion. With this space, here's your vaporization, right? Vaporize, meaning to make it into a gas. So vaporization. So the heat of vaporization is larger than the heat of fusion. Sure, yeah, when we look at this chart, the heat of vaporization is actually bigger than the heat of fusion, meaning it takes more energy to vaporize it than it did to freeze it. So it might be B. I'm going to check the others just in case. It says the boiling point is lower than the freezing point. No, that can't happen. It's impossible to have a boiling point, so going to a gas that is lower than it would be to go from solid to liquid. And the substance is definitely not water, so B is the best answer for this one. Number 6 is about the same one, so I'll keep it on this slide. It says which transition will release the most energy. So the transitions are occurring at the flat parts, and so the question is, does the first transition or the second transition release more energy? Okay. Releasing energy means, let's see, if we're going up, we have to put the energy in because temperature is increasing. So releasing energy means it's going to be going down on the graph. So a solid to liquid would be going up, so that's not A. Gas to liquid would be going down, and that would have a lot of energy because this line is longer than this one. The liquid to gas would be going up in energy, and liquid to solid is down, but it's less energy than the gas because this line is bigger. And that's pretty common. Most things, it's easier to melt it than it is to vaporize it. So I guess I'll pick B for number 6 here. Okay. Number 7. This is from the solutions chapter. It's a mass percent. So if we look at the formula sheet, we would see that mass percent has this symbol. Okay, and it means mass of solute divided by mass of solvent. So typically masses are used in grams. Oh, not solvent on the bottom, sorry, solution. The only one that has just solvent on the bottom is molality. Okay, there. Again, I don't want you to memorize that equation. That's in your formula sheet. Just realize that when I have something like mass percent, so if I have a concentration unit, then I want to look on that little table. And so we dissolved 4.15 grams of NaCl. Okay. It's going to need to calculate the molar mass, which is from the periodic table. So 58.44 grams per mole. That's our answer there. So I want to get that into moles because I'm trying to calculate. Oh, no, wait, I'm not doing a molarity. Hang on. I'm doing grams of solute, grams of solution. That's why I write this down when I see mass percent, just to remind myself what I'm trying to do. So I don't have to do this. That was wrong. So 4.15 grams of NaCl, that's probably the solute, and 65.1 grams of water. I know NaCl is the solute because it's less. Now, one common error, and I'm going to guess one of these answers would be correct for that mistake, is to just put 65 on the bottom. we said grams of solution, so that means I have to add the solute plus the solvent together to get that. And then that whole fraction is multiplied by a percentage. So we get 69.25 on the bottom. And so it's going to be about 6%, it looks like. 5.99277. So I'm going to pick answer B is the best choice there. Okay, so that's that. Next page is going to be question labeled number 8. They're all numbered funny, so but I'm just going chronologically in the questions here. What is the molarity? Okay, molarity is another one of those formulas. That's a concentration. So I'm going to look on the sheet and I see that it's moles of solute divided by liters solution. Not multiplied by 100%, it's not a percentage, just a funny unit that we use in chemistry. So moles of solute divided by liters of solution is the formula for molarity, and it equals the big M. That's what molarity is. We dissolve 4.15 grams. Oh, look, I can use that thing I just calculated. Awesome. So it's NaCl again. I'm not going to recalculate it, I just did it. Okay, so we can, I know I've got to get to moles because it's a molarity question rather than a mass question. So that's the logic I'm using there. And so it's 0.0705 moles of solute. And let's see, it's still 65.1 grams of water. And they give us the density now, and I'm going to guess that's because I have mass and I need to get to volume. That's usually the case. So 65.1 grams of water. And we're going to convert that using the density provided. And then I'm going to convert it into liters because I need liters. You know, maybe we should add, I think we're going to add together the total. So that way I know that it's liters of solution. I think that'll be easier than trying to go back and calculate after. So we had 69.25 grams here. And I'm going to divide that by 0.9874. And then I'm going to convert that from milliliters. So basically we're canceling milliliters there, we're canceling grams there, and we get liters. So it's 70.1 milliliters, and that means that it's 0.0701 liters. So I just take 0.0705 moles divided by the liters of solution and look for whichever answer is closest. It's going to be close to 1. Yeah, 1.005. So maybe I guess I'm going to go with D because it's the closest to 1. It's not exactly the same exact answer I got, but that's, you know, multiple choice questions are like that. Maybe they didn't add them together, I don't know. But that's okay. Number 9 is next, right? I think. Yeah. Okay. So number 9 is we make 250 milliliters of 1.43 molar solution NaOH. Oh, we want to do that. Okay. And you have 6 molar NaOH. Ah, okay. So I'm taking something concentrated and I'm diluting it. There's a key word in there. It says dilution, right? So there's an equation. It's quite handy to use. You could go all the way through the mole calculation, or we can use the dilution equation, which allows us to just sort of plug stuff in. Either way you go, whether you go all the way through the stoichiometry, you know, basically calculating moles and, you know, figuring things that way, or whether you use this, you'll get to the same place. It's just faster to use the dilution equation. So then I just have to start assigning things. The first molarity is the one we're starting with, which is actually 6 molar, right? We're diluting it, so we want to put the most concentrated thing there. We're trying to find V1. We don't know how much of our first stuff to put in. M2 is going to be our final concentration, which is 1.43 molar from the question. and V2 is I need a total of 250 milliliters. I don't need to do any unit conversions. I don't need to find molar mass. All I gotta do is plug it into this equation, so that's nice. Alright, so on the right hand side we're gonna get, my phone just turned off, there we go, calculator. 1.43 times 250, so we get 357.5. The units don't cancel, so it's still molarity here and milliliters there. But to get rid of this 6 molar over here, I'm going to have to divide both sides by the 6. And so then our molarity is going to cancel and just leave liters behind. So, milliliters rather. So V1 is 59.6 milliliters. So that would be answer A. Question 10. Which of the following will dissolve in water and create a strong electrolyte? Okay, so this is like the lab. Strong electrolytes are ionic salts that dissolve, acids and bases. There's only a few select strong acids. The one that we had in lab was HCl. Bases are strong if it's from group 1 or 2. And has an OH. There's only one exception. Lithium hydroxide is a weak electrolyte, not a strong one. So, but the rest of them are all strong. All right, let's see here. My choices are sucrose, C12H22O11, that's sugar. We know sugar is a covalent compound. It is not an acid, because the hydrogens are not written in the front, and it's not a base because it's not group 1 or group 2 with those oxygens and hydrogens. So A is a classic example. We mixed sugar and it was not an electrolyte, so A is non-electrolyte. B is magnesium and chlorine, so that is ionic. That would be a strong electrolyte. C is methane, also called natural gas, which is just carbon and hydrogen, so that is also a non-electrolyte, just like the sugar. And H2 is, well, that's just a covalent bond also, so non-electrolyte. The only one that would even make ions at all is B. 11. What is the pressure of a gas if there are 0.431 moles? We've got a volume. Okay, so we have moles. This is another gas problem. We don't know what the gas is, but that's the number of moles. The volume is this many liters. And temperature, so we're going to need to convert because it's a gas problem. This is where I have to remember that it's 0.2 and not just, 0.1. Because I have a tenths place there on this one for real. So our temperature is 337.3. Okay. And the question wants us to find pressure. So when I look at my equations, I find the ideal gas law. The only thing I don't have already written down is pressure, which I'm trying to find, and R. R is one of the constants that's provided. It's got funky units. It's just the ideal gas constant. So I can plug this all in. So a lot of you like to rearrange first, which I'm fine with. So we're going to divide by the, oops, not the pressure. We're trying to find pressure. I'm going to divide by the volume so that we can just plug in the numbers once and not worry about it. So, I'm not going to write units. You should when you do these calculations if you're showing me your work. But I don't have space on the computer. We said our temperature was 337.3. It's important to write your units when you do these calculations yourself, because if you've done it correctly, if you've rearranged this correctly, everything will cancel except for the atmospheres because we're looking for a pressure. Alright, so 0.431 times 0.08206 times 337.3, and then all of that equals 11.9, and I'm going to divide it by 4.16. So we find that the pressure here in this situation is about 2.87 atmospheres. Well, that's a little bit higher than I wanted it to be. 2.87 atmospheres, which is answer D. exactly. So that's good. Number 12, last multiple choice. Calculate the pressure of dry oxygen collected over water if the total pressure is 1.04. Oh, so this is like the molar volume lab. And in that lab, we used something called Dalton's law, which says that the total pressure equals the pressure of all the stuff. So in that example, I think we were doing oxygen, and water evaporates, so there's a little bit of water vapor there, and we got to account for that in order to figure out, how much oxygen we actually make. So this is kind of similar to that. The total pressure here is 1.04 atmospheres. And it says, and the vapor pressure of water is 21.4. Oh, 21.4 torr is going to have to be converted because, well, I guess, or you could convert this atmospheres. Either way works. But because we have to have the unit be the same in order to add them together or subtract them from each other. So it doesn't matter which one you convert, you'll get to the same answer in the end. 0.02816. So 82 atmospheres. Alright, and so we're trying to find the pressure of the oxygen. We already know that the water is this many atmospheres. So basically I just subtract 1.04 minus 0.0282. And so as it turns out, it's 1.01 atmospheres, which is answer B. Cool. All right, number 13, arrange in order of increasing IMF. So we want to go increasing IMF. So again, that order is LDF to dipole, then hydrogen bonds. Again, the name's a lie, it's not a bond. And finally, what's next? Oh yeah, ion dipole is usually the strongest. Now there's some overlap in these, but this is generally true. If a molecule is nonpolar, it's going to be LDF. If it's polar but doesn't have H connected to an F, an N, or an O, then it's going to be dipole-dipole. Ion dipole is something that's ionic, and it's got to be mixed with something that has a dipole. Okay, so like water is one example of that. If you have something ionic mixed with a nonpolar thing, then it's not going to be ion dipole. Alright, so those are the criteria. Our choices here, HF. HF is going to be a hydrogen bond. Whoa, what's going on there? Okay, hang on. I got too many lines. Sorry, computer freaked out for a sec. There we go. So HF is going to be hydrogen bonds, so it's going to be on the high side of things here. NaCl, well, it doesn't say it's mixed with anything, so that would actually be like an ionic bond, which is really strong. It wouldn't, I don't have room to write it where it would be on the scale. It's really strong though. CH4 rather, is non-polar because it's tetrahedral, so that means it's symmetric. H2O has hydrogen bonds also. When I'm thinking about this, the structure in my mind is this hydrogen like this. There's two of them. There's two hydrogen bonds in water, and there's only one in HF, so this one's going to be stronger. So when I rank these in order of increasing strength, we're going to go CH4 is the lowest because it's just LDF. HF is next because it has one hydrogen bond, water has two, and NaCl is going to be strongest by far because that's actually a bond, not an IMF really. It's an ionic bond. Okay. And our last page here, number 14. How much heat is required to change 4.16 grams of ice? Oh, okay. So it says heat. The only place we talked about heat was the dealy things that look like this. So for water, yes, we're talking about ice, so that's 0 degrees. The boiling is going to be at 100 degrees, and this is heat on the bottom. I like to draw this little diagram. It doesn't require it in the question, but it's a really handy way to orient myself. So if we have ice at negative 14, that's right here. So we're starting there. Okay. And it's going to be liquid at 1.5. That's not very high, but it's right here. Whoops. Now, the thing to remember about heat problems in Chem 142 is we already did the easy ones in 141, so any heat problem we have now is going to be multiple steps. Here's one step. There's a second step all the way across that area, and there's our third, right? So for me, I like to label the diagrams just to keep me straight. Right, so each heat, Q is heat. The slanted parts, we use this equation because the temperature is changing. So for, I guess, 1 and 3, we're going to do that. For Q2, it's just heat of fusion because that's the melting point. That's the amount of heat required to melt this stuff. So we look at the formula sheet. Okay, so it says heat of fusion is 335 joules per gram, so we can use that. Okay. Oh, well that one's an easy one to do because it's just dimensional analysis. I know that I have 4.16 grams of ice, so I can just multiply 335 times 4.16. We get 1,000. Let's see, so we got 3 figures. It says 1393.6, but I'm going to round that to 1390 because of significant digits. And that's going to be joules. Q1 is when we go from negative 14.3 up to 0. So our mass is still 4.16 grams. This is frozen water, so it's not the 4.184 value. We want to use the 2.06 here because it's ice. 2.06 joules per gram degrees C. Again, the units help you here because grams should cancel and our temperature should cancel. So it's not going to be the entire temperature change from negative 14.3 to 1.5. It's just going to be from the negative 14 up to 0 because that's where the ice counts. Okay, so our final temperature is 0 degrees, final minus the initial temperature of negative 14.3. So our temperature is going up, so it should be a positive number, but this is how you get there. Okay, and so Q1 is going to be 122.5, it says. I'm going to round that to 3 significant digits, and that's in joules. Q3, similar deal, same mass, because melting something doesn't mean you get more of it. But now we have a different value for our heat capacity because water absorbs more heat as a liquid than a solid. And then our temperature change, it ends at 1.5, so that's our final. And our initial for the liquid water was 0. Alright, so smaller temperature change. And so overall we get 26 joules. So the answer to the question, the total, is going to be 1390 joules. So most of our energy was spent in melting the ice. That's pretty common. Unless we're boiling as well. Boiling also costs more energy rather. So we just add these together and we find out that it's 1,539 it says. So 1,540 joules would be the correct number of significant digits. Oh no, wait, we're adding. I'm wrong. Never mind. When we add its place value, everybody has a ones place. Although technically that's not significant, but I would be alright with either 1,540 or 1,539 joules. I probably wouldn't mark you off for that sig fig. Alright, so that's 14. 15. Okay, so first it wants us to draw the Lewis structure, then find the geometry, and then decide whether it's polar or nonpolar as a molecule. So CO2. Well, carbon's in the middle because it's the first letter. The first one is always the central atom unless it's a hydrogen. If it's hydrogen, it's going to be your second atom. Because hydrogens can only connect to things once. Oops. I'm skipping steps. I'm not even telling you what I'm thinking. What's the point of that? Alright, so there's a couple different approaches to making Lewis dot structures. One that is really helpful for people in 112 is to first just connect everything with a single bond. And we have to have a total number of electrons. So I use the periodic table, and I find that carbon's in group 14, so it has 4. Oxygen's in group 16, so it has 6 each. So we've got 12 plus 14. Total electrons, not 14, 12 plus 4. So we got 16 total electrons. Right now I've only used 2, 4. So we're going to go in and complete the octet for everything. So that means I have 8 around each thing. And I like to complete the octet on the outside first, just because the central atoms can sometimes have more or less than 8. We have some exceptions that happened. Right now, carbon is not one of the ones that ever has exceptions. Its neighbor boron can, but not carbon. Carbon always likes to have 4 electrons, and right now it's only got 2. 2, 4, 6, 8, 10, 12, 14, 16. I do have the right number of electrons right now, but I don't have the right number of electrons around carbon. Carbon cannot have only 4 electrons. So if I take 2 of these and put them between the carbon and the oxygen, now the oxygen still has 8, 2, 4, 6, 8, and now the carbon's got 6. If we do the same thing on both sides, then you get 8 for oxygens and 8 for the carbon, so everybody's happy. Alright, so this is the best Lewis structure. There are 2 domains. They're both bonding. So we're just looking at the central atom when we're trying to find shape. It's just about the middle. So here's one domain, there's another domain. So they're both bonding. That means this has to be linear. If you only have 2 domains, you can only make a line. You can't do any other shape. Okay, so that answers the molecular geometry part. And so if it's polar or nonpolar, okay, so in order to determine that, we have to figure out, is it symmetric or not? Linear things, if these atoms are the same thing, which they are, linear things are symmetric, which means it's nonpolar. That does not mean that the bond is nonpolar. Carbon and oxygen have a polar bond. I think its difference is, 3.5 minus 2.1. So it's a pretty significant polar bond. But they point in opposite ways. So here's one dipole, here's the other one. And so they cancel each other out. So as a whole, this molecule is nonpolar because it's symmetric. It doesn't matter whether I cut this way or diagonally, whatever, it's still symmetric. Okay, so that's the logic. If there's any asymmetry, then the molecule would be polar. CH4, oh, we run into this a couple of times today. Carbon's going to be in the middle, and I connect everybody with a single bond to begin with. And then I count out my atoms and see if, or my electrons, and see if they're correct. Carbon has 4, each hydrogen has 1, so we should have 8 total. 2, 4, 6, 8. Now you could also, of course, you could draw it as dots. So this is review from 111. Either one of these ways is fine. But the important thing is I have 8 electrons, and I'm showing that here. Then it wants us to come up with a shape. So if it's got 4 bonding domains, then it's going to be tetrahedral. Tetra means 4. Tetrahedral is symmetric in all ways. Hopefully you're remembering your Vesper lab and the models that we built. So when you make something that's tetrahedral, you can slice it in all kinds of directions, and it's symmetric. So again, since this is symmetric, nonpolar, snap. Asymmetric is polar, is the last half of that. Okay, so let's see. H2O. We said that usually the first atom is the central atom unless the hydrogen is there, in which case it's not. So then we'll put oxygen in the middle and hydrogen on either side. Oxygen has the 6 electrons and each hydrogen is 1, so we should have 8 total. Right now we've only got 2, 4, so hydrogen can only handle 2 electrons. That's a contracted octet. It can only handle 2, just like helium. And so we're going to have to put more electrons on the oxygen in order to place these 8 electrons that we have. But that's good because actually oxygen wasn't happy anyway. It has 2, 4 that are in bonding. Oh, I'm going to change my pen color. So 2 bonding domains, 4 total electrons. And then we have 2 non-bonding domains also. So the electronic structure, so in other words, the electron orientation would be tetrahedral because there's 4 total domains. But the molecular geometry is going to be bent because these 2 non-bonding domains don't have atoms on it. So basically, the molecule actually looks kind of like that. Okay, so this looks symmetric on the Lewis dot structure, but a bent structure has the electrons on the top like that. So a bunch of negative charge on the top and the hydrogens on the bottom. That means this is not symmetric. You could also say asymmetric. That's probably the better word for that. But bent is always polar because it's not symmetric ever. Right? And there's a couple of ways to get bent geometry, but so those are really common geometries you should be able to recognize. Okay, so if you have any questions, feel free to send me an email.